So good morning, everyone. I am Sukriti Gautam. I'm a PhD scholar from IIT Ropar, India. And today I'll be presenting my work titled Low Power Bluetooth Low Energy Relay Node Operation in Mesh-like Architectures for Precision Agriculture. This work has been co-authored by Dr. Suman Kumar, who is an associate professor at the Department of Electrical Engineering at IIT Ropar. Now, in this presentation, I'll take you through the introduction, the existing solutions and limitations, the proposed methodology, experimental evaluation, followed by the conclusion. Now, moving to the introduction. So in this work, the targeted application domain is that of precision agriculture, which is essentially a modern farming approach that uses technology to monitor and managing crops, thereby reducing the manual effort. So this is a typical precision agriculture framework in which there are multiple sensor nodes that are laid across a field. These sensor nodes are battery powered and they are periodically fetching data from sensors interface to them. This data is sent by these sensor nodes using a low power wireless technology to a central device, which is a gateway which could optionally be relaying this data to a cloud server for further analysis over Wi-Fi or cellular technologies. So because the nodes are typically spread out, the data is actually propagated in a hop by hop fashion in these networks. So let's look at the relevant existing data propagation solutions. So the most popular solution used in the literature is the clustering based data propagation, in which the sensor nodes actually organize themselves into clusters, and periodically a cluster head is selected from each cluster whose responsibility is to collect the data from all the cluster members. And then these cluster heads, the several cluster heads across the network are going to communicate among themselves in order to convey the aggregated data to the base station in multiple hops. Now, the limitation here is that, number one, the cluster head operation itself is power hungry because this node is going to have additional responsibilities. Secondly, the cluster head election process is also power hungry because the nodes need to communicate among themselves, taking a lot of constraints into account. Now, in this work, we use Bluetooth Low Energy as the low power wireless technology. So I'll be talking specific to BLE. So the Bluetooth core specification has actually introduced a BLE mesh specification in which the sensor nodes themselves are not going to take care of the relay operation. Instead, they introduce external relay nodes into the network whose sole purpose is aggregating and forwarding the data. Now, one important information is that in BLE mesh, the mode of communication can only be advertisements, which is essentially a broadcast kind of a communication in which no connection is taking place between the peer devices. The limitation of mesh is that advertisements are an asynchronous mode of data transfer because essentially only broadcasts are taking place, and hence at the relay node, the reception is taking place in an asynchronous, non-deterministic manner, and thus the BLE mesh specification itself suggests that you always keep the scanning operation on these relay nodes, and hence it is also recommended that you power these relay nodes externally. So basically you continuously power them using an external source. But in outdoor deployments like precision agriculture, where you could possibly have a large number of relay nodes, this is not really feasible. So what we propose is that you go for a cluster and mesh based hybrid kind of an approach, in which, so basically in precision agriculture, the sensor nodes are going to be static. So we propose that you divide the entire area into smaller clusters. And just like BLE mesh, you introduce external relay nodes and you assign one cluster to each relay node specifically, from which it is going to collect the data. And then again, hop by hop, the relay nodes are going to convey it to the destination node. What we propose here is that in order to allow these relay nodes to run on batteries, we propose a relay node framework, a relay node operation, which does not need to scan continuously, which actually happens in a conventional BLE mesh operation. So as a result of this proposed methodology, the relay nodes are going to wake up at precise learned instance of time to capture data from specific nodes. And upon receiving each packet, they are going to return to sleep. Now, the proposed solution is designed and validated on commercial off-the-shelf devices in which the lower layers, the link and physical layers, are typically closed source, and hence we cannot really modify them directly. So the only option that we have as end users is to steer the functioning of these lower layers at the application level while strictly adhering to the rules defined by the Bluetooth core specification. So that's what we do. We at the application layer, we make the relay node to learn the pattern of the incoming packets. So I'll just quickly take you through the proposed relay methodology, which has been implemented at the application level, and it uses HCI commands and events, which are a part of the BLE stack. So the proposed relay node application operates in three phases: learning phase, time difference updation phase, and the scan and sleep phase. So when the relay node is initially booted, it executes the learning and time updation phase sequentially, but only once. And the rest of the operational cycle is spent in the third stage, which is the scan and sleep phase. So coming to the first phase now, the relay node is going to stay in the first phase for as long as it has not received at least one unique packet from all the nodes in its cluster that has been assigned to it. Now, as soon as it receives a unique packet from a node, it is going to record the system uptime value. The system uptime is actually how much time has elapsed since the system of this relay node was initially booted. Now it is going to make a record of all these system uptime values. And then once it is done recording all the M nodes, it moves to the second phase, which is the time difference updation phase, where it is essentially only going to calculate the differences of the consecutive uptimes. These values are going to give it the intervals at which it is supposed to wake up and receive the packets of specific nodes. Now, I would just like to mention that there are some special cases under which learning phase could yield such uptime values, which could lead to wrong interval values being learned in the second phase. So second phase is also going to take care of those cases through some backup mechanisms. Now, once all of this is done, the node is actually ready to enter the scan and sleep phase, where what it is going to do is, as per the learned intervals, it wakes up, receives a packet, and this system is designed such that the disabling of the scanning operation gets automated. So as soon as a packet is received, the application is going to trigger scan disable. So that's what takes place throughout the third phase. I'd like to mention two things specifically. One is that throughout the third phase also, when upon the reception of each packet, the relay node is actually again going to record the uptime values and update the difference values, because there could be clock drifts taking place at the sensor nodes which are transmitting. Secondly, it does not really wake up at the exact intervals that it has learned, but it opens the reception window a little bit earlier to accommodate again for two cases. One is that there could be clock drifts taking place at the sensor nodes, and the second one is that the sensor nodes are always transmitting duplicates of the packet because they are operating in a broadcast kind of a mode. And thus, the first packet to be received at the relay node could actually be any of these duplicate copies. So in order to take care of these two cases, it is always going to open the reception window a little bit earlier. Now, in this entire methodology, we also inculcate backup mechanisms for two special cases. One is that now, as I said, the disabling of scanning operation is actually automated based on when a packet is received. Now, what would happen if the reception window was opened, but nothing was received, right? So we need to give it some other trigger. So that is one thing that we take care of. And the second thing is that due to clock drifts taking place at the sensor nodes, the initially learned pattern of transmission could actually change over time. So the relay node should also be able to detect this pattern and adapt accordingly. Now, we did some experimental validation of this architecture. So we conducted some real-world experiments to check the battery life of the proposed operation, and also to check what is the sync efficiency that can be achieved when we use this particular methodology at the relay nodes. For this, we carried out 7 days of outdoor field experimentation. So these are the battery life results. For these calculations, we actually used the average current consumption values using the NRF power profiler kit by Nordic Semiconductor. So these are the battery life values. So if the cluster size is large and the transmission intervals are small, the waking up at the relay node is going to be more frequent and the battery life is going to be smaller. So if you see, even for the cluster size of M equals to 20, and for small transmission intervals of 20 seconds, the battery life exceeds 1 year. So the performance was pretty good. And these were the data reception experiments. So what we did was we actually deployed 2 clusters of 6 nodes, and we used 2 relay nodes. One was the working as per the proposed mechanism, and the other one was the standard mechanism in which the relay node never sleeps. So we compared the performance of these two kinds of nodes through 7 days of continuous experimentation. So these are the results. So you can see that the proposed nodes A1 and B1 perform pretty well. They achieve packet reception rates comparable to those of the standard one, and they also reach 100% sometimes. So in conclusion, I would say that through this work, we have demonstrated that BLE advertisements can be leveraged to enable low power and reliable operation on commercial off-the-shelf devices when the operation is entirely driven by the application layer. This will allow reliable field coverage without frequent battery replacement, and this is especially very helpful when the transmission intervals are large and the nodes are fewer, because otherwise, if you use the standard operation in such cases, your node is going to be on unnecessarily for a very long amount of time. And as the future direction, we are conducting further studies to study the performance of synchronous BLE advertisement mechanisms in similar operations. These are the references. And that's all. Thank you.
Okay.